Okay. So, we will do bit of okay. This symmetry breaking is a very important concept in particle physics as well as in condensed matter physics. In fact, all sorts of physics. So, yes, symmetry breaking. So, I will explain what that is, and Goldstone mode. Okay. So, this is what I will have 3 modules, but we start with this module first. So, discrete symmetry. So, there are many examples, but the one which I have done so far, I will take that example, which is Ising spin. Okay. So, Ising spin Hamiltonian is without magnetic field. Okay. If there is no external magnetic field, then it is minus j S I S j. J is the coupling constant, which is coupling between 2 spins, right. So, we have spins on a lattice, and this spin interacts with neighbors. So, this spin interacts with 4 neighbors. This is so we compute total energy by summing over all spins, but interaction is only with the nearest neighbors. Okay. So, that is our Hamiltonian. Now, this is Hamiltonian is a scalar. Now, you can see that this object SISJ take value plus and minus 1, right, or right, it is up spin or down spin. Now, you can see that it is symmetric under if we change the spin to all, I mean change the sign of a spin of all the spins, then the Hamiltonian remains unchanged, right. So, of course, we have to change sign of all spins. So, symmetric under SI to minus SI, right. So, it is called up down symmetry. So, that means, if I have Ising system where if spins some are up and some are down, then you compute energy. Now, we just reverse the roles, down becomes up and up becomes down, the energy will still be the same, right, because this product is symmetric under my S 2 minus S. Okay, so, Hamiltonian is symmetric, but what about the solution? Is the solution symmetric under S 2 minus S? No, because ferromagnet in this either they are under after phase transition, either they are up or down, right, all of them are up or all of them are down. That means, the symmetry is broken, right. So, the symmetry is broken in a ferromagnetic solution. Of course, paramagnetic solution is symmetric, I mean half are up, half are down, but in a Ising spin, the ferromagnetic solution has this symmetry. Symmetry is broken. Sorry, symmetry is broken. Okay, is that clear? So, this is called symmetry breaking. Your Hamiltonian respects symmetry. But solution does not. Of course, this is a discrete symmetry, it is not a continuous symmetry, because it is either 1 or minus 1, right. Yeah, there is no in between. So, it is a discrete symmetry breaking. Okay. So, this is a simple example. Of course, there are many examples, but like so this is a up down symmetry, or you can have parity. Parity is always plus or minus 1. No? So, that kind of spins. But now, let us look at another example, which is again discrete symmetry. It is does not it is not continuous yet, but this example is very important example. So, I take a scalar field phi and I write down the Lagrangian. So, this Lagrangian is relativistic Lagrangian. Okay. So, let us stick to relativistic. So, this means d by dt of phi squared minus grad phi squared, right. This is a Lorentz scalar. Okay. So, we will do Higgs mechanism where we need it is done for relativistic. So, I am just going to keep that. So, and u is a potential which is function of phi, and we take phi 4 is phi squared plus phi 4, right. So, this we have seen it for a statistical physics example, we did full theory, renormalization group. Now, is this Lagrangian symmetric under phi going to minus phi? Yes, symmetric, no, phi going to minus phi, they are all quadratic or quartic. So, that unchanged. So, Lagrangian is symmetric, but what about the solution? Now, look, I am also telling you that we are looking for a asymptotic solution, we are not looking at time dependent solution. When the system is reached equilibrium and we are looking at that state. So, the potential, so we will look for constant solution. Okay. So, I can write down equation of motion, and this equation of motion will have set d by dt to 0. Okay. So, this is the potential. So, where will it like to go? The system will go to minima. So, for constant solution this derivatives will go to 0, right, and we set not potential is not the u phi to 0, but derivative of u phi with phi is 0 minimum. Okay. So, we want to set du by d phi to be 0. Okay. So, take the derivative of this. So, what is the derivative of du by d phi? So, mu squared phi plus lambda factorial 4 is 24 lambda, derivative of 4 5 quarter phi to the power 4 will be 4 phi cube. So, this becomes 6. So, this is the solution, the equation, not yet the solution. So, now what is the solution for this equation? Phi equal to 0 and phi squared equal to minus mu squared by lambda, or phi equal to square root of this plus minus. Okay. So, this we have done it, this is the phase transition, Landau theory. So, when mu squared is positive, then both these terms are positive, but lambda is always positive. Okay. We assume lambda to be positive. So, u phi is for both mu squared and lambda positive, this is the potential, but when mu squared becomes negative, then it becomes inverted parabola, and but of course, for very large phi it should go to infinity, positive infinity. So, we get this, and for this case the stable solution is this. Okay. For the left case, stable solution is phi equal to 0. In fact, there is only one solution. When is it? Mu squared greater than 0, but for mu squared less than 0, there are 3 solutions, this one and this one, but among them which is stable or which are stable? The one at the lower minima, right, they are stable. In fact, you can prove it, these unstable. Okay. So, this proof I will not do, but you can do the stability analysis. This solution is stable for mu squared negative, but this is phi equal to 0 is unstable, and that is theory of Landau transition. Okay. So, these are now what does this example tell us? My Lagrangian is symmetric under phi going to minus phi, but my solution is not. Okay. But this is again a discrete symmetry, you are changing the sign. Okay. So, okay. Now, let us look at continuous symmetry now. So, here I need to make this expand this field phi. Okay. So, this is a picture of what I want to do. So, I take 2 scalar fields phi 1 and phi 2. So, again Lagrangian has the time derivative component and the space derivative component, but we set it to 0, right, we are looking for a constant solution, and u phi. So, x axis is phi 1 and y axis is phi 2. Okay. So, earlier I was plotting phi as the axis, but now I have 2 fields. So, I plot phi 1 phi 2. Now, my potential, my Lagrangian is this. Okay. So, these are the I have 2 fields. So, I write down exactly same form as a scalar, but I add them. Now, my potential u is again similar form, but except instead of phi squared I have phi 1 squared plus phi 2 squared, and here it is phi 1 squared plus phi 2 squared squared. Okay. And I put a minus sign. Okay. So, I am following the book by this gifted amateur book. So, this minus sign is put. So, here for mu squared positive we will get a non-zero solution, okay. But that is up to you, you can choose either way. So, what is this, how do I get the solution? So, by the way, this system is better to use phi I mean basically phi r, which is square root of phi 1 squared plus phi 2 squared. This is azimuthal symmetry, you know. So, this angle, well I should call it theta not phi. So, this theta, if I choose some angle theta for between this one, this my potential is unchanged. So, it is better to use phi r as a variable, then my potential is minus half mu squared phi r squared plus 1 by 24 lambda phi r to the power 4. Okay. So, the analysis is pretty similar, except now phi r is, we will get value for non-zero value for phi r. And what is the value for phi r or non-zero value? So, that means the radius. So, you can see this is a hill. Now, you go down and the distance of the hill from the minimum of that surface. So, your surface is like is called Mexican hat, okay, or any hat, not any hat, but you in India also you can find this hat now. So, this is a hat where you have this circle for which where it is the function is minimum, right, that the circle is here. And what is the radius of the circle? The radius of circle is will be finding the minimum of this, and phi r will be pretty similar. So, that is what did I get? So, I take the derivative mu square phi r plus 1/6 lambda phi r cube. So, 6th there is a minus sign 6 mu squared by lambda. Okay. So, that is the radius of the circle. Okay. So, but important point is now it has, so when mu squared is negative, when this is this quantity becomes positive and this becomes positive, mu squared is negative, we will have both the quantities positive, and this you do not be Mexican hat anymore, it will be paraboloid, or not paraboloid, is some paraboloid will be only this part, okay. But it is a pi squared plus phi 4, but it is some function like that which is minimum at 0. But as soon as I make mu squared positive for this example, then I get a solution which is unstable solution at the hilltop or any point on the circle, right. Any point in the circle is a solution. Your system can lie there and happily sit there forever. Agree? This is a solution. I mean, so my solution is independent of this angle theta. In fact, that is a stable solution, any point on the circle. Okay. So, this is called continuous symmetry. Okay. So, my solution right now has a first, okay, before going to that. So, what is the symmetry of the Lagrangian? So, phi r, okay. So, this part I would write, so here this angle theta, my Lagrangian is independent of this angle theta, right. So, if I write in terms of this angle, so phi 1 will be phi r cos theta and phi 2 will be phi r sin theta. Okay. So, when I sum the squares, it becomes independent of theta. So, that is a continuous symmetry, this Lagrangian is independent of theta. Okay. And by the way, my solution will pick one theta. When I look for the asymptotic solution, it will not be everywhere, it is not a quantum system, it is a classical system, it will find some solution, some theta, okay, that is where it will find itself. Okay. So, my solution for this case will be phi r, and you can choose any angle and theta. I may choose theta equal to 0, the stable solution. Okay. Now, here my symmetry is broken. Why? Because my solution was, my Lagrangian is symmetric under theta transformation, okay, independent of theta, but my solution is 1 theta. Okay. So, this is symmetry break. Okay, it is all right. So, there is another example which is given in mechanics books. So, we keep a rod, vertical rod. Okay. Now, you apply force at the top. If you apply small force, it will remain there, no problem, but if you apply too much force, then it will bend along some direction, right. So, that direction will spoil the symmetry. The vertical rod has symmetry with azimuthal symmetry, it can be anywhere. Well, it is not function of phi, but after it is bent, it has, the symmetry is broken. Okay. So, I hope you understand that there is continuous symmetry for the Lagrangian, but the solution breaks the symmetry. Okay. So, and one more point, that if I take a solution at this point somewhere here, then if I shift the particle along that circle. So, there is a circle of minimum u, and is not looking a circle. So, let us make a slightly better circle. So, if I start from here and I shift it here, is there change in potential energy? No, right, this is the same potential. So, here in fact there is, when I go along the azimuthal direction, there is no change in energy. So, you can equivalently write, you can write down the Lagrangian in fact, by the way, in terms of the new variables, and here for this part. Okay, so, I must say that, okay, so for this part mass is 0. So, which is a mass term here in our Lagrangian? So, I think it is important to make this emphasis. This is a mass term. Okay. So, mu squared phi squared, the coefficient of phi squared is mass term. Now, I can rewrite this equation in terms of phi r and theta, right. So, in fact I rewrote like that. So, you can see that phi r squared has a mu squared coefficient in front, but theta is a new variable. So, theta squared has nothing in front, in fact it is 0. So, what is the coefficient in front of theta squared, which is 0. So, that means the mass corresponding to this azimuthal rotation in the Lagrangian is 0. Okay. So, this is called 0 mass along the azimuthal direction, and this is called Goldstone mode. Okay. Breaking a continuous symmetry leads to massless excitation. Okay. So, my solution is now here, and this excitation is massless, and this is called Goldstone mode, and particle associated with this symmetry is called Goldstone boson. It has a 0 mass, that is what you should remember, it has no mass, like photon has a 0 mass. Okay. Now, let us look at another field which in fact we need it for our later slides, complex scalar field. Right now, what I should have 2 fields, phi 1 and phi 2, but I am going to combine them, and I say, well, let us make a field psi, and psi dagger is for one component object it will be just complex conjugate, right. So, instead of phi 1, this is phi 1 squared plus phi 2 squared in the past, but now I just write a psi star psi, but in practice we write a psi dagger psi. Okay. So, it could be multi component, right, I mean it could be a vector. So, psi dagger psi, and we can also generalize it easily to fields, rather not, so complex quantum fields. Okay. So, this is a pretty similar, except now this is psi and this is psi dagger. Now, complex field has psi real plus psi imaginary. Okay. So, these are the 2 components you may think, or you can say psi and psi star, you do not need to write psi real plus psi imaginary. psi and psi star are two independent fields. In fact, we have done that kind of thing in the past. When we derive the equation of motion, we can use derivative with psi star and get equation for psi. Okay. So, either you can treat psi r and psi imaginary as independent variables, which is more complicated. I mean, you have to rewrite this as psi real plus psi imaginary, or treat psi and psi star as a independent variables. Okay. Now, what is the solution for this object? So, first this Lagrangian is symmetric under this transformation psi exponential I alpha, yes, because look at this term. So, you will get first psi e to the power I alpha, and what about psi dagger? I get psi star e to the power minus psi dagger e to the power minus I alpha. So, e to the power minus alpha I to I alpha will cancel. Alpha is a function, okay. Alpha is function of x, but it is a single object function, not a matrix. Okay. So, they will cancel. Similarly, here also this is symmetric under all this transformation, then this also will be symmetric. What about these guys? You can look at it here. So, del mu psi e to the power I alpha. So, it will become del mu psi e to the power I alpha plus, now mu will act on that psi e to the power I alpha del mu alpha. Okay. So, I get I am getting what do I get? E to the I alpha will be there, and I get del mu psi plus del mu alpha. Okay, there this part is problem. Okay. Now, so alpha has to be constant. Okay, for this case alpha has to be constant, because this will spoil the symmetry. So, I think let us start this part from scratch from beginning. So, let us take this Lagrangian, which is generalization of last example, not generalization, it is a rewording. I mean change of variable. Here it is psi dagger psi and psi dagger psi squared. So, this Lagrangian is symmetric under this transformation, but alpha is a number. Okay. So, you can see that psi dagger will be e to the minus alpha and this e I alpha, they will cancel. If you rotate by an angle of the every field, all the fields. So, it is a global transformation, okay, and that is symmetric. But what about the solution? By the way, this alpha is like that azimuthal angle, no? Which the example of theta I was giving you is similar to that angle, but solution will be, well, this is our potential is very, in fact is identical to what the Mexican had, what we got there. So, here I will have to write psi real and psi imaginary, okay, and my minimum will be on a circle and whose radius will be square root mu squared by lambda. Okay. What is square root 6 mu squared by lambda. Okay. So, that is identical. I do not need to do that in detail, but we get similar results for this case.